Welcome to Brain Vision.
Okay, so for this question, let's apply the energy balance equation. So we have E dot in is equal to E dot out. If we expand it, we have Q dot in plus M dot H1 is equal to M dot H2. Q dot in here is the rate of heat transfer into the water, and M dot here is the mass flow rate for the water. H1 is the initial enthalpy for the water. H2 is the final enthalpy for the water. If we do some arrangement here, we have Q dot in is equal to M dot times H2 minus H1. So we know in this case, the mass flow rates can be equal to the density times the area and then times the average velocity, which is equal to rho times pi times d over 2 to the power 2 and then times v. D here is the diameter, okay? And rho is the density. So if we plug in back to the equation, we have Q dot in is equal to rho times pi times d over 2 to the power 2 times v and then times H2 minus H1. So in this question, since we know the water is not reaching the boiling point, so therefore the water is not turning into saturated liquid, which means that we can use the specificity of the water at a constant pressure. So we have H2 minus H1 is equal to Cp times T2 minus T1. T2 is the higher temperature, and T1 is T2 is the final temperature, and T1 is the initial temperature. So now we have Q dot in is equal to rho times pi times d over 2 to the power 2 times v, and then times Cp times T2 minus T1. So we know the density for the water is 62.1 pound mass per feet to the power 3, and we know the diameter is given as 0.25 inches, which is 1 over 48 feet. So we also know that the average velocity is 40 feet per minute. If we convert it to feet per hour, it's about 2,400 feet per hour. And we know the specific heat for the water is given as 1 British thermal units per pound mass times degree Fahrenheit, and the changing temperature is 35 degrees Fahrenheit. So now let's plug in back to the equation to determine the rate of heat transfer into the water, which is equal to 62.1 pound mass per feet to the power 3, and then times pi, and then times 1 over 48 feet over 2 to the power 2, and then multiplied by 2,400 feet per hour, and then times changing temperature, which is 35 degrees Fahrenheit. And this will give us the rate of heat transfer to the water is about 1778 British thermal units per hour. So now let's determine the amount of heat generated by the electronic devices mounted on the cold plates. Since in the question it was saying that the remaining 85% is removed by the cooling water, which is the heat transfer into the water. Okay, so therefore the total amount of heat that was produced by the electronic devices should be equal to, let's say, Q dot is equal to Q dot in divided by 85%, which is equal to Q dot in over 0.85. So now let's plug in the values. So we have Q dot in, which is 1778 British thermal units per hour over 0.85, and this will give us the total amount of heat that was generated by the electronic device is about 2,092 British thermal units per hour. And these are the answers for this question.